This lesson is over intervals of increase and decrease. Our objective today is I can determine when a function is increasing or decreasing. It would be helpful if you can print the note template that I have linked on Canvas. If you're unable to do so, you can either write on your computer or with your phone, like with you using your finger with the two colors that we're going to use today, or you can just copy the graphs onto notebook paper. When you do draw the graphs on notebook paper, you're welcome to just sketch them rather than draw out all the individual grid lines and labeling everything. You'll still get the point of the lesson if you're just sketching them. We'll also look at some real-world situations and kind of application of this context or of this characteristic as well. So let's go ahead and get started. What's going to be helpful today is if you have two different colored pencils, I'm going to choose green and red because we're talking about increasing and decreasing, but any two colors will suffice. So having two different colors will be helpful today. Maybe a pencil and a pen or two markers, something like that. So let's define what intervals of increase and decrease are. What intervals of increase and decrease are where a function is increasing or decreasing as it relates to its x values. Now, we look at the x values because our x values are an independent variable. So where a function is increasing or decreasing depends on what x value that we're looking at. So we're going to write an interval notation, which we're used to writing all the time. For instance, anytime I ask you to write domain or range, you're already writing an interval notation. So it's going to look very similar to that. So let's get started with our two examples. This is the first two of four examples we're going to look at. And we're going to look at quadratic ones first to get the idea. So this first graph I know is quadratic because it has that U-shaped curve, and I see a squared as an exponent. Remember that a squared function, anytime you see to that second power, that represents a quadratic function. So when I look at my graph and I'm reading from left to right, I notice that my graph initially, as I'm reading left to right, is decreasing. So I'm going to color that in red until I hit my vertex here. Once it hits the vertex, my function increases. Let's look at the other function. Again, I know it's quadratic because it's that U-shaped curve, and because I see a squared in the corner, or in the function. But this time, I notice as I read left to right, my function is increasing again to the vertex, and then it begins to decrease. So let's define what intervals they're increasing and decreasing over. I'm going to jump back to the first problem. My interval of increase. If I reference my vertex here, my vertex x value is at -1. So from -1 to infinity, my function is increasing. Now remember that this is referencing the x values, not the y values. So I know that the function is going up. We're not talking about end behavior here. We're talking about the interval of increase and decrease. So we're looking at just our x values. From -1 to infinity, my function is increasing. Now, we do not put a hard bracket on the -1. The -1 represents the turning point, and that turning point does not have increasing and decreasing qualities. It's just a point. Now, from here, from -infinity all the way to -1, my function was decreasing. So notice how in our final answer, we have the -1 reflected from the vertex, and we'll have an infinity and -infinity because our function in the x values can only go from -infinity to infinity. Let's look at our second example. From -infinity, let me write in green, -infinity all the way to 4, my function was increasing in this case. Increasing, hits my vertex. Then as my x values continue to get larger, it's decreasing. So from 4 to infinity, it's decreasing. Now you may be thinking, well, the function is decreasing, it's going down, so why isn't this -infinity? Again, we're just talking about the x values here when we look at intervals of increase and decrease. So from the x value of 4, and then 5, and then 6, and then 7, all the way up to infinity, my function is decreasing. Let's look at two more examples. So here we have a linear function with a quadratic function. So right now I'm going to outline my intervals of increase on my quadratic function. And if you notice, my linear function is increasing the entire time, and we'll take a look at what that means in a moment. And in my red, I'm going to highlight my decreasing part of my function. So my vertex of my parabola is 0, -1. I'm going to keep that in mind as I write my intervals of increase and decrease. From my x value of 0 all the way to infinity, my function quadratically is increasing. From here all the way up, as my x values get larger, my function is increasing. But from -infinity to 0, my function was decreasing in this case. -9, -8, -7, -6, -5, 4, 3, my function is decreasing the whole time until I hit 0, and then it begins to increase. Let's look at g of x now. Now g of x is increasing the entire time. So for our decreasing interval, we would just write none. There is no decreasing interval because from -infinity to infinity on my x-axis, the function is always increasing. Let's look at one more example. Here we have a quadratic function and an exponential function. Quadratic because it's that U-shaped curve, and exponential because it's a J-curve. Again, let's highlight our intervals of increase and decrease, and notice how this exponential curve is increasing the whole time, where our quadratic function has an interval of decrease in there as well. So let's start with our quadratic function. Our interval of decrease would be from -infinity to 0, because that's what our x value is. -infinity, it's decreasing this whole time, hits 0, then it begins to increase from 0 to infinity on our x values, infinity. Now, with our exponential function, as we read left to right, my function is continually increasing the entire time. So again, here there is no interval of decrease in this case, only increase. So from -infinity all the way to positive infinity, no matter what x value I pick, if my x values are getting larger, my function is always increasing. So let's take a look at this in a real world context. I just found two graphs I wanted to show you just to kind of give you an idea of why something like this would be important. And they both have to do with carrying capacity and environmental science. So for instance, this is kind of a graph of the carrying capacity of certain animals throughout the year in certain months. So we could look at the intervals of increase and decrease on this graph to kind of figure out when our populations are increasing, when they are decreasing during what months. And in this case, we could figure out, okay, well, if we're decreasing during these months, what are some reasons for that? Other examples of carrying capacity. This is just kind of a general graph, but you can have carrying capacities that almost have this. It's called this case would be a sine curve, which you'll learn about when you get to algebra 2. But these functions like this, if we're looking at when populations are increasing and decreasing, we can kind of study reasons why that is and make predictions about future populations.